This topic we're doing is a core pure topic, and I've said it's called Methods in Calculus in the textbook, but I've said it's chapter 3 and chapter 6. If you remember, chapter 6 was hyperbolic functions, but the bits we didn't look at with hyperbolic functions was differentiation and integration. So I've grabbed those parts of chapter 6 and I've put it alongside some of these things from chapter 3 because it's basically further integration. It's just more things to do with integration that will build on the stuff that we've been doing in regular maths. So we've now done enough integration from regular maths to be able to access these kind of things that we're going to be doing. Hopefully, this is core pure, yeah. Core pure 2. So hopefully the things we're going to be able to get through today is improper integrals and the mean value of a function. The mean value of a function I could teach you in about 30 seconds, okay? So that's going to be something that's very, very, very short, very, very, very easy. This thing might take a little bit longer to do. And then what we'll be doing over the following lessons is looking at differentiating things we don't know how to differentiate, which will include hyperbolic functions as well. And then we'll also be looking at doing further types of techniques with integration that will start integrating to things like arctan and eventually with hyperbolic functions and things in as well, okay? So that's the chapter 3, and it's also pulling in some stuff from chapter 6 because I think it makes sense to put some of those things together. But the first bit that we're going to be starting with is improper integrals, and I've got all of this printed for you, so really all we really need to do here is read through this together and think about what is happening, and we're going to try and work out what an improper integral is, and the way we're going to do that is by looking at 3 examples that do some kinds of weird things here. So the first thing I've said is, okay, we're going to determine the integral between 1 and minus 1 of 1 over x squared with respect to x, and is there an issue that we have here? So first of all, I've plotted what the graph looks like for 1 over x squared. Why do you think this is the graph? Are there any features of the graph you can tell me that, that you can see because it's 1 over x squared rather than 1 over x? What's different about? Yeah, because if it's being 1 over x squared, you're always doing 1 divided by a positive number, so you'll notice that everything here is above the x-axis, okay? So that's just what it looks like, and it's between minus 1 and 1. But look what happens when we integrate this. So first of all, we've rewritten it in its indices form. We've actually done the integration with the limits 1 and minus 1. And when you substitute in those values for 1 and minus 1, you get minus 1 minus positive 1, which is minus 2. Obviously, this area is not minus 2. Why is it cannot be minus 2?
Not under the graph.
Because it's not under the graph, okay? So I've said here, what's odd is that we ended up with a negative value, but the whole graph is above the x-axis. The problem is related to integrating over a discontinuity. It says, i.e. the function is not defined for the entire interval minus 1 and 1, notably where x equals 0. So we know if x was equal to 0 here, you get some kind of problem. You're going to get 1 divided by 0, and you get some kind of asymptote. It is undefined there, which means it is not a continuous function. A continuous function would look like this, where you can continually draw the graph. This is not a continuous function because there's one point where it is not defined. So we're going to see it says here, we will see when this causes an issue and when it does not. And we say here that the definite integral does not exist, okay? The second kind of thing that we might look at is to do with limits that involve infinity, okay? We're going to look at limits that involve infinity, like positive infinity and negative infinity. So here we're doing the same kind of integration, apart from we're doing it between 1 and infinity, and it says, is there an issue? So I've said here, the below is seriously dodgy maths, as we're not actually allowed to use infinity in calculations, and that's because there's different kind of sizes and concepts of infinity. So it looks like this would actually be equal to 1 for this particular graph, which is quite interesting because we're saying if you find the area underneath this graph from 1 all the way to infinity, that it actually has got a finite area. No matter how far you go along, the area is not going to get bigger than 1. But you can't actually do this substitution with infinity, and we're going to discuss how you were to do this. The answer actually is going to be 1. So I've said here, although the graph is extending to infinity, the area is finite. The area is finite. Even though it goes on infinitely, it gets so close to the x-axis that it's barely adding on any area as you move along in the x direction. And we'll see why that works. And this is because it says the y values converge towards 0. The result is therefore valid this time. This is an example of an improper integral. This is what we mean as an improper integral, something that's got like an infinity sort of sign in it. That was what we'd call an improper integral. And because the value converged, we say that the definite integral exists. So it could either exist or it could not exist. If it doesn't exist, it means it wouldn't converge to a particular value. I think we've come across the word converge before. When have we maybe come across the word? Pardon? Yeah, it's sort of to do with join together, converge. It means it kind of like narrows down and tends towards a particular value. Yeah. And what's the opposite of converge? Separate. No, diverge. Have you come across those words, converge and diverge?
Well, that explains the divergence theory, doesn't it?
Yeah. So if something diverges, I'm trying to think when we've done it, maybe when we did like series, obviously often the sums of series can often be divergent because they don't actually sum to a particular value, where you can have sum of series that converge to particular values. Then there's another type of one that we might look at, and it says here we're going to determine the integral of 1 over the square root of x between 0 and 1 with respect to x. And it says again, is there an issue here? What do you think the issue might be to do with the limits in this particular integral we're looking at before we read what it says?
0.
The 0, yeah, tell me more about the 0.
What's the square root of 0?
What's the square root of 0? 0, but that's not the problem.
1 divided by 0.
1 divided by 0 is the problem. And when you look at the graph, at 0, the graph is not defined. So we're trying to find the area between something that actually just keeps going up forever and ever and ever and ever and 1. But actually, it does have an area because it gets so close to the y-axis that it converges. So let's just read what it says here. You can see when you substitute in these different values, you can actually go straight to this bit here and you come out with the answer 2. And it says this is similar to the second example, although y tends to infinity as x goes to 0 and is not defined when x equals 0, the area is convergent and therefore finite. The result of 2 is therefore valid. But we would not write it in this particular way that we've got up here because of the fact that the 0 is undefined for that function. So it's just a couple of different things we're going to be writing about that we have for this different style of integration. And the 3 things we're going to be thinking about are if there is a graph that has a discontinuity in the middle of it, or if there is an infinity or negative infinity in the limits, or if in the limits, one of the limits refers to something that is undefined in the particular graph. So it says the integral that we have here is improper if either one or both of the limits is infinite, which is what we were just talking about, or if the function is undefined at a or at b, or if there is another point in the interval a or b where it is undefined. So for example, this one here is undefined at a, at the beginning part of it, and this one here is undefined at some part in between a and b. It's undefined at 0. So improper integrals are going to allow us to deal with this particular set of types of integration things that we've got here. Okay? So let's have a look at actually just doing a couple of these things here. First type of one we're going to look at is when there is an infinity symbol inside the integration. And this is the more formal way that we do this. So to find this, what you do is you get rid of the infinity symbol and you take it as a limit instead. So you can't use infinity in calculations, but you can use the variable t, and then we can see what happens when t tends towards infinity. And we've come across this idea of limits when we were looking at differentiation. It's all I've got written here. We've come across that when we use differentiation by first principles. So this first one that we're going to do here, we're going to try and integrate between 1 and infinity, 1 over x squared with respect to x. And we're going to try and either find out what it is, or we're going to show that it does not converge to something. Those are the 2 options that it can do. And the way that we write this is that when you integrate this, it is the same as taking the limit as t goes to infinity between 1 and t of 1 over x squared dx. So this thing, if I ignore this thing that I've got here, we can just do the integration on, and we'll leave it with t in, and then we'll think what happens when t goes to infinity. And that's a way of us avoiding having to write in infinity inside our calculation. But it does mean you have to keep writing the limit as t goes to infinity until you've actually taken that limit. So what does 1 over x squared integrate to? Minus x to the power of minus 1, and that is between 1 and t. So again, we need to write the limit as t goes to infinity, but this time we can now start actually substituting in the different things that we have. So that would be minus 1 over t minus 1 over 1.
Why can't we use infinity in our repetition?
Because
We used it when we done, like, let's say, inequalities with graphs.
so when we used those, we should have done those more formally using limits. You can use them sort of roughly to think like, oh, if this is infinity, the reason when we were doing that, and I said, oh, we can just pretend there's an infinity on the top and 2 infinities on the bottom, is because we hadn't really done much about limits at that point. And so if we had done stuff about limits, I would have talked to you about it like this, okay? But good connections with it, going back to what we talked about with inequalities. You'll be doing more in limits in FP1 as well with Miss Chalmers. So now, as t goes to infinity, what happens to this term that you have here? It tends to 0. It becomes so small. When this becomes infinity, this whole thing here becomes 0. So we can then go straight to what the answer would be. This would just become 1. That's your answer there. So despite it having infinite limits, it actually converges to a particular value, and the value that it converges to is 1, which is kind of crazy that despite it going on forever and ever in the x direction, the area has a ceiling. The area can't go above 1. It will never ever get to 1. It never get above 1.
But it's not actually equal, it's slightly below by the tiniest of margins.
Well, this is the point we're making here. It actually will be equal to 1 if you go to infinity. Can you get to infinity? No. No, but we can get to infinity because we're saying we've got to infinity. So it's this kind of paradox that we have here. We're saying you can never get to infinity to show that it will equal 1, but we can say it gets to 1 because with maths we can get to infinity. In real life we can't get to infinity, but with maths we can take it there, okay? So we're now going to try this second one here. We're going to evaluate this between 1 and infinity. This time it's 1 over x, and we want to show that it is not convergent. Or sorry, we're going to evaluate it or show that it is not convergent. So the limit between 1 and infinity of 1 over x with respect to x, as soon as you do that, you're going to write lim as t goes to infinity between 1 and t of 1 over x dx. We just tend to use t as the most common letter for this, okay? We just pretty much always use t. And what does 1 over x integrate to? Good, ln x between 1 and t. So we have the limit as t goes to infinity of ln t minus ln 1. ln1 is just 0. So we've now got the limit, and maybe I don't need to write this extra line, but we've just got ln t. Now what happens as t goes to infinity? What happens to ln t when t becomes really big for ln? Is there a ceiling on what ln t can become?
T tends to become 0, no?
ln(t) looks like this.
Well, no, there's not.
No, because this
It
can,
goes on
this
forever.
it keeps going on. It flattens off like an exponential graph, but it never flattens below a particular value.
There's no end point.
There is no ceiling. There's no asymptote like along the top like this. That does not exist for an ln graph. So as t goes to infinity, ln(t) also goes to infinity. So it is not convergent. And while you look at that, I'm going to just put both of the graphs on to just get a sense of what might look different about the graphs between 1 and infinity. Although I think because it's first day back at school, nothing is working very quickly. Okay, so we've got 1 over x and 1 over x squared. I mean, you can tell which one is which. Obviously, the red one is 1 over x. But there's just something about the 1 over x squared one, like it is hugging the curve, like much, not the curve, the axis, much closer. It's much closer to the x-axis. So the area between 1 and infinity of the blue one is 1, but between 1 and infinity of the red one is infinity.
Because it's just that slight.
Because it's just got that slightly bit more. Even though as you go like all the way over here, they're basically going to start looking the same thing. The area is kind of crazy to think that the area underneath the red one is infinity. Sorry, the red one is infinity and the blue one is 1. Between here and here. Strange, hey?
There's not infinity up to a point.
What do you mean?
Because that one will start hugging the x-axis as well.
But less so than the blue one.
Okay, but only
The
less
blue
than
one
and
will always be lower than the red one, and that's enough to give it a definite.
But wouldn't that one have like exact value as well? The red one.
No, because we've just shown it here. We've shown that this one, that as t becomes really, really big, this is what we said it will integrate to.
But after a certain point, like it will be so little, like just like the blue one.
But it will be significantly bigger than the other one that it looks like infinity.
That's the trippiness of this. Like, it's good that you're like not happy with this, Ibrahim, because this is what is weird about maths like this. But maths tells us that the area of it is infinite. Okay, we'll do a couple more, I think. Okay, so now we're going to look at some of them where f of x is not defined for some value. So like in the first example that we had at the very beginning of the lesson, where it was not defined in that central part. So it says here, we need to avoid values with the range AB for which the expression is not defined. But just as we avoided infinity by considering the limit as t goes to infinity, we can similarly find what the area converges to as x tends towards the undefined value. So here, we're going to try and evaluate 1 over x squared between 1 and 0 with respect to x, or show that it is not convergent, which is the value in the limits, or in between the limits, which is not defined. 0, yeah, because if x is 0, you will have 1 over x. So we know that at 0, the function is not defined here. So I'm going to say at 0, 1 over x squared, I should have said at x is 0, 1 over x squared is not defined, or is undefined. So if we want to go between 0 and 1 of 1 over x squared with respect to x, we instead need to do the limit as t tends towards 0 between t and 1 of 1 over x squared dx. Do you see there? We're not allowed to use 0 because we can't actually substitute in 0 into this graph, but we can do it with t and say, well, let's just do it with t and then see what happens as t goes towards 0. Because we can never actually make t equal to 0 because it's not defined there. Subtly different. And then we've just got its simple integration. and then some substitution.
Would you go?
So what happens to this as t goes towards 0?
-1 plus infinity.
Yeah, so you get -1 here, plus 1 over a tiny, tiny number is going to a huge number. So this thing here tends towards infinity. So does it converge? No, it does not converge. So, I mean, in normal maths, we would probably want to explain this a bit more, but in further maths, you can get to this stage, and we as further mathematicians know that this does not converge. Just in normal maths, we would normally write something like this. We would probably say, as t goes to 0, we would say 1 over t goes to infinity. I mean, that's probably a good thing to say, but if you don't say that, none of the examples in the book show them saying that explicitly, but I still think it's probably a good thing to say. We get as t goes to 0, -1 over t goes to this, so we get the whole thing would be equal to, say, it does not. It does not converge. So you've got -1 plus infinity. The whole thing is going to infinity. So the area underneath this between 0 and 1 is infinity. And actually, if we look back at the graph, we're now saying for, let's just get rid of this one, for the blue one, between 0 and 1, this area inside here is infinite. But this one under here was 1. Strange, but interesting. And I'm sure we might be able to make a prediction. Maybe this one has a finite area. I don't know. Maybe it does.
Well, isn't it symmetrical by the...
Yeah, good point. It's symmetrical, so it's probably not going to, is it? Okay, so for this last one of this section here, and then we'll do what maybe, I think we'll get all the examples out of the way so we can just do some practice. What's the issue in this one that we've got here? Good. At x equals 2, it is undefined. So at x equals 2, x over the square root of 4x squared is undefined. Now, you could have done this one here without using this limit notation. You probably could have done this one like it was in one of the earlier questions, but you wouldn't get any of the marks, okay? Because this question will come up to check, do you understand when you need to use this limit notation, okay? If you just did this, because I mean, technically you could have just done, maybe not this one, but you could have just done it without the limits in, like here, like this one. It just looks like it works and it gives you the right answer. Yeah. But you wouldn't get any of the marks if it was in the exam because it's an improper integral, because it's not defined here and you haven't used limits. So you have to show that you're using limits here. The whole theme of this is using formal maths. This is a very formal kind of topic here. So you must make sure that you're using limits for this. So we've said that when x is 2, it's undefined. So we're now actually going to say between 0 and 2, I'm actually just going to probably rewrite this as x brackets 4 minus x squared to the minus a half with respect to x. We're going to say it's the limit as t goes to 2, because that's the thing we're not allowed to work with, between 0 and t of x 4 minus x squared to the minus a half dx. So we've got the limit as t goes to 2. What does this integrate to? Can you spot what rule this should be? Or what rule this shouldn't be, maybe?
Is it a series stuff?
What, for integration, what?
Yeah.
It's the reverse chain rule.
I didn't even know that I said that.
Why is this the reverse chain rule?
Because x is a differential of x squared.
Good, yeah. This is the derivative of the thing that's inside the brackets. Yeah, it's the derivative of the, or it's a version of the derivative of the blah, isn't it? The derivative of the blah in here is 2x, minus 2x, and this is an x, so that's good. So what does that mean then we think it's going to integrate to? Not necessarily the final answer, but what type of thing should it integrate to? What's the thing that we would consider? You know, we do our consider then scale, if you're in my class.
Yeah,
Pretty
it-
fried.
You're in his class, sharp.
Sharp number. 4 minus x squared and the power of a half.
Good. And now we just need to scale it to the correct kind of thing, okay? If we were to differentiate this, you would bring the power down, which is a half,
Times the derivative.
and you times it by the derivative, which is minus 2. So you've got a half times minus 2,
It's got minus x.
So
So
it'd
times
be-
by minus.
so you have to times it by a minus. And that's between 0
And the limits.
and t.
2.
So we'll substitute
So
these.
with, I know this is normal maths, but with reverse chain rule, right?
Yep.
Whatever the derivative is, yeah, you look at where the other thing, and then you consider that and scale from there.
Yes. Yeah, this is the main part of the function, and this is the thing that's been spewed out as a result of the chain rule.
Okay.
Yeah, so it's like, this is the function that I'm like, I did the chain rule to, and this is what I got as that extra thing that came out, because you know when you do the chain rule, you get the derivative
Yeah.
of the blah. So that's why I just look at the main function, I increase the power by 1, and then scale it, blah, 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 okay? So when we substitute in our values, we then get, I still have to write this annoying bit at the beginning, the limit as t goes to 2, you get minus 4 minus t squared to the half minus what becomes a plus 4 to the half. And what does this all equal? 2. Because when you say that t goes towards 2, this thing goes towards 0, this thing goes towards the square root of 4. So this one actually does converge, and it converges to 2. We're going to look at 1 or 2 more examples, I think. And then we're just going to do some practice. I mean, that's it, really. So it does converge, and it converges to 2 because this thing here collapses to 0.
Can we see that one?
Yeah, sure. So we've got 4 over the square root of 4 minus x squared. No, x over the square root of...
When you do the square root of 4, though, you don't hit the minus, you can't hit the minus value, can you? You have to hit the positive.
Yep, because it doesn't have a negative in front of it. Okay, so we're evaluating it between, what do we say, 0 and 2. Yep. And actually, just like visually looking at it, it looks like it's like really, really close to it at that point. So you can see it kind of makes sense that this looks like a finite kind of area that we have. But you can't look at it and tell. You can't use the graph to tell you, but you can use the graph to then get some kind of sense of meaning from it afterwards, okay? So we've just got one last thing to look at, because I believe actually what we've done so far is we've looked at it where one of the limits is infinite. We've looked at it where it's undefined at a particular point. The only thing we haven't looked at is if both of the limits are infinite, and possibly if there's an undefined bit in between. So you just have to be careful where you do this. So I want to integrate something between negative infinity. This is a very weird number line I've drawn. I want to integrate something from negative infinity all the way up to positive infinity. And the way that I'm going to do this is I'm actually going to do it as 2 separate things. I'm going to do, if I want this blue range of limits that I've got here, I'm going to do it as 2 separate integrals. I'm going to do as one of it from minus infinity to 0, plus from 0 to infinity. So if we wanted to do it between negative infinity and infinity, we would evaluate this by saying that negative infinity to infinity of f of x would be the limit as t goes to negative infinity between, so that would be t and 0, f of x. Whoops, forgot my dx. So this is going to deal with our from negative infinity to 0, plus the limit as t goes to infinity between 0 and t f of x dx.
For dx and stuff.
Oh, I forgot the dx at the very beginning. Yeah. Very bad of me.
Wait, what was the bit in the middle?
So this is, if you think about it, we're going between minus infinity and 0, and then between 0 and infinity. Yeah. And I guess in theory they could ask you one where there was something undefined in there as well. So you'd have to do,
A few more integrals.
you'd just have to, if it was undefined at 0, I guess you'd need to use another letter. You'd need to do, I don't think they'll do that.
'Cause then we have
They'll
to
probably do it
do
in the exercise.
t to minus
If we say, I don't think they will do that.
Let's do this one here and then we'll do some practice, okay? Because we've done a lot of me talking here. So first thing it says is we're going to find the integral of x e to the minus x squared with respect to x. Notice it's got no limits, so it's not even asking you to do anything to do with this topic yet. And then b, it wants us to show that it converges to a particular value when you go between minus infinity and infinity. So what is the integral of x e to the minus x squared dx? What's this going to be? Integration by parts? Is this going to be reverse chain rule? Like what kind of thing is this going to be? Do we think substitution?
Substitution.
Chain rule again.
It's chain rule again.
Or that.
Yeah.
This is our main function, and the derivative, the blah part that you're going to get, we've got e to the blah. The derivative of the blah is minus 2x, which is a form that's related to x, because you can just scale it. So what does this...
In this respect, when you say blah, you mean the part e to the power of it?
e to the blah, yeah. Because that's when we use the chain rule, yeah? So e to the blah, the derivative of that blah is minus 2x, which is a form of this that we can do some scaling. So we know it's going to integrate to e to the minus x squared, because that's just how it always works with e functions. But what would we need to scale it?
So that 2x or a half and a negative.
Good. Negative a half e to the minus x squared plus c. Are we all okay with why it's negative a half?
Yeah.
Because if you differentiate the power itself,
If you just differentiated that,
you get minus 2x e to the whatever the hell. Yeah. And you want to get rid of the half because you want to.
yeah, if you differentiated that, you get minus 2x e to the minus x squared. But I don't want minus 2x e to the minus x squared. I want x. So you multiply it by minus a half, okay? Now we know what it integrates to. We can actually go to part B. And part B is now going to be doing it without limits between minus infinity and infinity, x e to the minus x squared dx. So that's going to be the limit as t goes to negative infinity between t and 0, x e to the minus x squared dx, plus the limit as t goes to infinity between 0 and t, x e to the minus x squared dx. I'll pause at that point so you can get some of that written down, and if you've got that written down, you can probably just do the rest of the question, can't you?
I'll skip to the next step.
So we've still got to keep writing our limits in until we actually evaluate those limits. And we've got minus a half e to the minus x squared between t and 0 plus the limit as t goes to infinity. Let's go straight in with that. Minus a half e to the minus x squared, 0 and t. And then if we sub these values in, we've got the limit as t goes to minus infinity when you put 0 in, you get minus a half, and then you've got plus a half e to the minus t squared plus the limit as t goes to infinity minus a half e to the minus t squared plus a half.
What?
So hopefully you've got to this stage here.
It cancels out to 0.
Everything cancels out to
Yeah.
0. Because I just want to talk before what actually happens here. As t, just ignoring this second limit that I've written here, as t becomes negative infinity, what happens when you square negative infinity?
It just becomes infinity again.
It becomes infinity again, and so you're doing e to the minus infinity. What's e to the minus infinity?
One, it's
Think of the e graph. Think of your e to the x graph. And send yourself to the negative infinity side of the x-axis. 0. Look, e to the x is like this. If you go all the way down here in the negative, it tends towards 0. So this thing is going to... Yeah, this is going to tend towards 0 when t goes to negative infinity. And because it's being squared, this thing is also going to tend towards 0 for the e graph. So you just get minus a half plus a half, which is 0. And look at the graph. Oh, I can't zoom in on that graph, so I'll put it on Desmos because I copied it in the wrong way. And you get x e to the minus x Why is it equal 0, the area between minus infinity and infinity?
Because they are the same.
What are the same?
The
The bumps.
Yeah.
The areas, the area,
Below.
yeah, the area under this and the area here would be a negative version of that. It's symmetrical. We're going from negative infinity all the way to infinity. So the areas will cancel each other out and we come up with 0. What about if it was just between 0 and infinity? What do we think the area is? A half. Good. It's a half. This is minus a half. So there's nothing, this can sound silly for me to say this, there's nothing new here other than the language of limits, of us just saying that you're not allowed to substitute infinity in. You are allowed to substitute t in and then think, how does it behave when you go to those particular extreme values that you might have? So we're going to have a look at exercise 3A here, and we'll take a little break and do some questions.